Okay, well, welcome to the session on savings and in this case, specifically compound interest. I'm Bill Bosshardt. I'm the director of the FAU Center for Economic Education, and I will be leading you through just a few ideas about how to teach about saving, but most importantly, this idea of compound interest and then how savings accumulates. And so that's what we'll be doing today. So thanks for joining, and here we go. So number one here is, what we're going to be doing today is number one, illustrating compound interest, talking about how you teach that to students. Number two, talk a little bit about the math of compound interest. It's not difficult, but and students can do the math. And so this is just going to be a review of going through, and teaching and showing the math. We are then going to cover the rule of 72, and it's been my experience that either people are very comfortable and know about the rule of 72, or they've just not heard about it or used it. And so we'll talk about the rule of 72, what it is, and then we'll also talk about how you might use it and apply it. And then lastly, we'll talk about, well, why is it so hard for people to save? And so we're going to go ahead and show you the video of the marshmallow test. I'm sure a lot of you have seen the video before, but nonetheless, it'll give us an idea. It's a great illustration of why it's so hard for people to save. And then we'll talk a little bit about discounting, which is really another fancy way of saying, why we sometimes fail the marshmallow test. Okay, so here we go. In terms of illustrating compound interest, there are videos out there, right? So you can get a number of videos illustrating, compound interest and how things grow. I put the link for one here. I'm not going to show it because it's a fairly straightforward one from, I think, Investopedia. But nonetheless, you may want to take a look at it if you are looking for a video just that just goes and just talks about compound interest. Instead, I'd like to just sort of talk about other ways of presenting compound interest in your classroom. So number one, the easiest way I think when we talk about compound interest is this idea of doubling idea, and really doubling is compound interest, right? And so there's a lot of different versions of this kind of story, but we're going to go with a dollar, starting with a dollar. Sometimes it's a penny or whatever, but you have a dollar, and every day what you have is doubled, okay? And so that's the same as that, that's really saying the same thing as you are being paid 100% interest per day, right? Loan sharks would love that, right? 100% interest per day. In other words, you're doubling your money every day. And so, so this is, an example of compound interest, right? To show that, right, you start out with the initial dollar or the principal. So you have that initial dollar and you have that principal. And then on the second day, you have then, principal plus then the interest. And so you have the principal that you start out with. And then you have interest, right? So you have an extra dollar, you have $2, right? So principal plus interest there. Okay, now with compound interest, then when the next day comes, right? If you're using compound interest, you're going to get double the $2, right? And so basically what you're getting is your principal plus interest, and then you're getting interest on your interest, right? And so here we go, right? So this dollar, is then doubled, and then also this interest that you're getting is then doubled as well. And so what you are getting here is then your principal, which you've always had. You get your new interest on this principal, right? So this dollar is your principal. You get new interest because it's another day. And then you have your prior interest. And then here's the last dollar, right? This is your interest on the interest, right? So you can see then, okay, there's interest on that interest. That represents compound interest, and that is the benefit that you get. Now, if you had simple interest, well, okay, what would that be, right? Simple interest then is that you don't get interest on the interest, And so what happens is that if you had simple interest at 100%, well, it would look the same the first round, right? You would get your dollar, your principal, and then you'd get your interest. But then on day three, it would change, right? Because yes, you would get your principal, you would get new interest on this principal, and you would get your prior interest. But because it's simple interest, you don't get the interest on the interest like you would with compound interest. And so you can see, of course, in this extreme example, right, when you're doubling something, of course, the compound interest really accumulates fast. But you can see here that you get considerably less. You only get $3 instead of with compound interest, you would get $4. Okay. So, this, of course, if you went more days, you could see it makes an even bigger difference as time goes by. So simple interest basically says, well, look, all we're going to do is we're going to pay interest on that original principal each period of time, each day. And so you get $1, $2, $3, $4, $5, $6, $7, because the interest on that first dollar is all you're getting each time period, right? You're not getting interest on the interest, you're just getting interest on that original principal, and then that's it. Compound interest, right? Well, then yes, you're getting interest on the interest. So it's $1 to $2, and then you get double, right? Because you're getting that interest on everything, principal plus that extra interest, to 4 to 8 to 16 to 32 to 64. So you can see, of course, then compound interest is really is really the way to go. But once again, interest is pretty high, right? We have a pretty high interest rate here and every day. Obviously, it is an extreme example, but nonetheless, compound interest does work, particularly because especially when people go over a longer period of time, it starts to accumulate. Well, let's look at a little bit the math of the compound interest. So we're going to use some symbols here to represent different parts of what we're going to come up with as a formula, right? And so P is your principal, that's your original amount deposited. R is going to be, and this is going to be important, nominal. Okay, nominal, use that term, meaning just not adjusted for inflation, is what you see on your statement, whatever the interest rate that the bank is paying. Annual interest rate, and usually we're just going to put it in decimal form. So 5% would be 0.05, for example. Okay, so that's our nominal interest rate in years. Okay, right, annual in years. And then T is going to be our time, how many years you're going to have, and we're the T is in years because we're using an annual interest rate. And then N is the number of times you're going to compound that each year. And A will be then the amount you have at the end of the time period of however long you want to hold your money in there. And so what we're looking for is a formula that tells us, okay, well, what is A going to be, right? So if we hold our money for this length of time at this interest rate, how much will we have? And that's the goal of what we're trying to do here for compound interest. So let's go ahead and do the calculations. And your kids, right? Your kids have had their algebra, so this actually won't look very foreign to them. For those of us who've been a little further away from our last math course, this will require a little review, but it comes back pretty quickly. And so here we start out, T equals 0. The first time period, we just had that initial deposit, P. So that's our principal. So that is how much the principal is. And then in 1 year later, right, we have our principal, and then we have the interest, and you take the interest rate times the principal, and that gives you your interest. So we have principal plus interest, and we factor out that P out of each one. You can write it as P times 1 plus R, right? Okay, so far so good. Okay, so what do we do here? Well, we go ahead for the next period. So this is how much we have. And so what are we going to do? In the second time period, well, we have the same amount of money, and then we get the interest on this. So to get the interest on this, all we do is take R times this same amount, right? So this thing here, right? This is how much money we had time 1 times R, the interest rate. That gives us then the interest for this period. So you can multiply this out, right? And so P, RP, and then we have another RP, and then we have PR squared. So you have P 2RP, and we have R squared P. And these are actually important terms, right? The P is our principal, that's the original amount of money. 2RP would be the amount that we would have if we had simple interest. And then what does compound interest? It adds this R squared P. Now, you say, okay, well, this looks complicated. Well, we can simplify this. We factor out the P, and then you factor the thing, and you get 1 plus R squared, right? And your kids actually will know how to get from here to there. So we have P plus 1 plus R squared. And so what we have then is, okay, the makings of a formula here, right? So the 2 is the number of periods that we've had the money in this account. So the formula is this: the amount that you're going to have after a set period is going to be equal to your principal times 1 plus the interest rate in decimal form raised to how many ever years that you have, right? And so we are assuming R is your annual interest rate, T is the time in years, and that it is compounded annually, right? Okay, so this formula, you'll see, you go on the web and you say, oh, what's the formula for compound interest? This is going to be one of the formulas. But what happens if we compound a little more often? Okay, what happens if that, we compound monthly, let's just say? How does that change things? Well, okay, so this is the formula for annual compounding. If you want monthly compounding, then, okay, well, what do you do here? Well, instead of R, right, being the annual interest rate, we want then, because we're talking about months, we want the monthly interest rate, which is just R divided by N, right? This is the number of months in a year that we're going to be using. So you take R by 12, right? So your monthly interest rate would just be your annual interest rate divided by 12. And then here, because now we're compounding over monthly, you take the time in years times the n, which is now which is number of months, 12, and then that gives us the total number of months that you want to compound. So does this make a difference? If we compound more often, does it make a difference? Do we get more money? Well, yeah, we do, right? Because we know, compound interest is, the benefit is interest on the interest. So the more often you compound, the more you get interest on the interest. It's going to give you a little bit more money. How much of a difference? Well, let's take an example. So $1,000 at 12% annual rate. So annually it would be 1,000, and then we go 1 plus, well, our interest rate is 0.12, 12%, and just for 1 year, just raised to the 1, okay, that is 1,120. Now, if we compound monthly, then what do we do? Well, here for our interest rate, we put our monthly interest rate, 0.01, and here then we put the number of months that we're going to be going, which is that for a year is 12 months. And if you do that, you see you get 1,126 and 82 cents. So you can see that by compounding on a monthly basis, you're actually getting an extra $6.82, for this. And so that's not a bad deal, right? I mean, you prefer to have more frequent compounding because it will give you just a little bit more in terms of your interest. Okay, you say, well, I want lessons, right? So those are examples, right? The doubling examples are things that that you can easily use in the classroom. But if you want some lessons that will help the kids, we do recommend Next Gen Personal Finance Materials, and so Next Gen is a website which is dedicated to teaching financial literacy. And so you go to Next Gen Personal Finance, and you all are from Palm Beach County Schools, and I know that Aaron Standish has probably introduced you to the Next Gen Personal Finance website, or certainly will in before you get done with this boot camp. But you go to their things, you search for compound interest, and you find this math. Calculating compound interest lesson, and it's kind of it's kind of fun, in the sense that the kids can go there, and then they have a little game, and so part of it is just using the formula, right? And so trying to figure out so what it does is it's just a game, and you have to sort of match, the number with the appropriate, letter, corresponding letter. So you have this problem here, right? And then it asks, to ask you to match, based on the problem, what's the interest rate, and then you match the interest rate with, the things. And so it's kind of a fun little game, right? So you match the variables, and then you figure out the things. So you can send the kids here, and they can practice, matching the numbers, knowing, what the interest rate is, what is R, what is this, based on the problem, and then, coming up with the correct answers and things. So once again, this is some place that, you can send them to sort of practice, using these calculations. And I always think it's very important. I mean, most of these things, of course, I mean, you have online calculators and whatnot, but, I always think it's important that the kids know, where these things come from, especially some of them are going to be able to do the math and understand the math. It gives them sort of the idea of where these things come from, and it reinforces their math education as well. And so I always like to sort of go ahead and take a look at that. Okay. The second thing then, that I think is important when you talk about compounding, is the rule of 72. And this is important in the sense that it gives people a little bit of a sort of a sense of how long does it take for things to grow. And so the rule of 72 works like this. It basically tells us how long it takes something to double, right, in size, when you're given in this case, an interest rate. So if you're asking how long does it take for money to double when the interest rate is a certain amount, the rule of 72 is very useful for that. So how do you use the rule of 72? Well, the rule of 72 is pretty easy. Basically, you take 72 divided by whatever your interest rate is, and that will tell you, the result will tell you how many years it takes then for your money to double if you just left the money in the account and it was compounding. So, so for example, right, if so you had an interest rate of, say, 12%, well, 72 divided by 12 would tell you that after 6 years, you would then have double your money. And so that gives you an idea of then, how long it will take in terms of, your money to grow. But in terms of like longer things, like retirement, and it gives you an idea of really how important it is to sort of start early. And so here we go. Here's so and it really does make a difference. It also sort of places importance, or tells the student how important it is that you have a good interest rate or rate of return on your money, because you can see that if the interest rate is 2, well, 72 divided by 2 is 36. It takes 36 years to double. So if you have your money in a savings account at a bank, or a CD in a bank, and it's running 2% or something like that, it's going to take you 36 years for your money to double. And that, of course, is a very long time. And in fact, I mean, yeah, it's almost not worth having the money in the account. But you can see then, even an interest rate of, as we said, 6. 72 divided by 6 is 12 years. Well, 12 years is a long time, but it isn't 36, right? And so that makes a difference. And of course, if you have then an interest rate of 10, it's about, well, 7.2, roughly 7 years before it doubles. So obviously, if you get a higher rate of return, it's much more important. To give you an idea of this, right, of how this doubling works, and why it sort of gives you this sense of how things go in life, and why saving early is important. My current sort of favorite example is of compounding and using the rule of 72 is this idea of baby bonds. And so so people have been concerned, of course, that, well, we have this wealth gap, and and so that's in a concern to many people. And so there's an article here. This was written by Annie Lowry. She actually wrote also a book, Give People Money, which talked about universal basic income. So she's very much interested in, well, how can we close the wealth gap, and look at inequities in our society, and how can we figure out how we can sort of fix those kind of issues. So she's proposing this idea of these baby bonds, and so it works something like this. Now, this is not a new idea. I mean, this idea has been around, but the idea is, well, okay, well, look, I mean, let's use compound interest, right, as sort of a to our advantage, because when somebody is born, they have a lot of time in their life, and that means there's a lot of time for interest to accumulate. So let's give an example. Well, okay, suppose we give $4,000 to a kid, when they're born, right? So 4,000 at birth. And then we have an interest rate of, say, 8%. Well, what will happen, right? So first you say, what? Give 4,000 to every kid born. Well, okay, well, first of all, I mean, that isn't a lot of money, okay? $4,000. About 4 million kids are born a year, and it's going down, right? It's getting cheaper because the birth rate's going down. Is $16 billion. And if you look at the federal budget, and here's some numbers. Okay, they're in the trillions, right? And this is 16 billion. Okay, so it isn't a huge amount of money. But to give you an idea of what's the potential, right? If these bonds are given, well, what could happen, right? So at age 0, it's 4,000. Now, okay, what? It's going to double every 9 years. So 72 divided by 8 is 9. So every 9 years, that money is going to double. So at age 9, it's $8,000. At age 18, that's 16,000. So it may be then this is the kid's college education right there, right? So there's money, and no, it's not an entire education, but 16,000 starts to go a little ways towards making it easier for somebody to attend college. If for some reason the money isn't spent at that point, and it's continuous, it's 32,000, right? Maybe a house at age 27, maybe that's a house down payment. Age 36, 64,000. Okay, don't have any event there. Age 45, 128,000. I just put it in divorce settlement. No, maybe not, but 120,000 starting to get be a bit of money. Age 56, 54, 256,000. You get to age 63, you're thinking about maybe retirement. That's $500,000, right? So if the money hasn't been touched over that period of time, and the average rate of return is 8%, that's a fair amount of funding, right? For somebody in retirement. And if they wait sort of until maybe age 70, we're getting to $1 million or so. I guess that should be 72. Now that I'm looking at it, I guess you got to wait till 72. That isn't quite 9 plus 63. Don't know what I was talking about there. Okay, so but same idea. You're talking close to $1 million for retirement. So so this idea of giving these bonds to kids, and then letting compound interest grow the money so that helps people later in life, right? Because we all know, right, when we're talking to your students, well, you do reinforce the idea that you want to save early, but the fact of the matter is that by the time they're 18, they've lost 2 doubles, right? So you say, oh, there's a double, there's a double. There's opportunities, right, for money to be growing, on their behalf. Okay. You say, well, 8%, where am I going to get 8%? It's not really, a stretch to say 8%, right? If you look at a broad-based mutual fund kind of thing, S&P 500, you can see then the average rate of returns from 1928 to 2019, or 16 to 19, or 2008, right before the recession, to 2019. You can see the average has been around 11, 10 to 11%, roughly about 11%. So, a rate of return of 8% is not really outlandish to sort of say that that might be an average rate of return over the long run. Now, of course, this is an average over long periods of time. There will be times when, it goes down, but there'll be times when it goes up. And so the key here is that, when you're talking about investing over the long run, we're talking about then, averages. And so, S&P 500, of course, is better than Treasury bills, but even at Treasury bills, you look like you're getting 6% or something. Okay, so, I always like to, and now thinking about my own self, it's like, well, I'm now 58, and so how many doubles do I have left? Well, I think I have about one more double. So when I look at the amount of money that I have, and if I want to want to retire in 9 more years when I'm 67, I probably have one more double left. And so it is sort of a convenient way of thinking about, okay, here I am now. Okay, well, what will I have, in the future? And you can do those, back of the envelope kind of calculations. Okay. Now, the second thing then that we want to talk about is a little bit is that after we talk about compounding is then, how do we get people to save? That's an important kind of idea here. And one of the things, that I always like to use to illustrate why it is difficult to get people to save is the marshmallow test. And if you've seen the marshmallow test, you'll know what it is. For those who haven't seen the marshmallow test, it's fairly self-explanatory. Now, of course, our video and electronic setup isn't so good here, but I'm hoping this will work just okay, that you'll be able to hear. There isn't much to hear, but it does give you an idea. So I'm going to make sure my speaker is turned up to the maximum so that you have best chance of hearing it. Good. And I will start it here. There we go.
Okay, sit in that chair. All right, here's the deal. Marshmallow for you. You can either wait, and I'll give you another one if you wait, or you can eat it now. When I come back, I'll give you another, so then you'll have to. But stay in here and stay in the chair till I come back, okay? All right. I'm gonna go do something, and then I'll come back. It's yummy. It's really good. All right, so it's up to you. You can have it now or you can wait. Okay? I'll be back. Stay in the chair, okay? Okay. All right, so I'm gonna leave and then I'll come back, okay? So you can either eat it right now or you can wait. Either way, okay? Okay. How'd you do? Did you do good? You did? You wanted to eat it, didn't you? Yeah. So I'll tell you to give me another one. Okay, I even have both. You need.
Okay, so that is the marshmallow test. Um, there's other videos. I put another link to another version of the marshmallow test. It has a little bit more background information. And they actually, this was an original experiment that was done, I believe in the late 1960s. And then they followed the kids and they correlated how they did on the marshmallow test with future outcomes like schooling outcomes and whatnot. And they found correlation, right? The kids that had could wait, tended to perform better. And so, so this was a very famous set of things. But it does show us that, why it's so hard for people to save, because here you have these kids and they're getting, 100% interest rate off by waiting for, I think it was maybe 10 minutes or so. And yet it's difficult for them, and it's difficult for all of us to worry about that. Now, the marshmallow test has been done repeatedly, and recently, of course, some of these new studies are now suggesting that maybe your child isn't doomed if they fail the marshmallow test younger in life, but when they're young in life. But nonetheless, it still is a good illustration of why individually all of us do have problems saving, right? And that makes it more difficult here. And so, well, why is it, that we don't, we find it hard to save? And, economists call this the idea of discounting, right? So the marshmallow test basically is really an example of discounting. And discounting is this idea that economists have that, well, look, humans value things less in the future than they do today, right? And so if you receive something in the future, then its value is discounted, right, for you today. You'd rather have a dollar today, you'd rather have a marshmallow today than you would want in the future, right? And so anything received in the future is worth less. Now, this concept of discounting you can find at the Council for Economic Education, Econ EdLink, the Center for Economic Education is a part of a network, and our national organization is the Council for Economic Education. And at their Econ EdLink, they do have all sorts of lessons, and you'll see the link here, and that will direct you to a lesson on discounting. I'm just going to show you a little brief version of it because we want to keep these videos at a reasonable length. But the idea of discounting is just simply with this graph here. And so this illustrates, the idea of discounting. So for example, in this example, it's basically saying, well, look, every day in the future that you get something, it's discounted by half, right? So it's saying that $10 today, right? Well, okay, if you get $10 in one day, it's not worth $10 to us today. It's only worth $5, right? So $10 given to you one day from now maybe is only worth $5 to you today. Or, something $2 is only worth $2.50. And so the problem with getting things in the future, i.e. saving, right? Because saving is putting things off to the future, is that, well, we value things less. And you can see that, of course, depending on how much you discount, it can be worth quite a lot less, in terms of how you value things. So this is called exponential discounting. Every single day in the future, it gets worth less and less. There's other types of discounting. Present bias discounting basically says that, you have either today or the future, and you just discount anything in the future the same, right? So $10 today is worth $10 given to me anytime in the future. You say, well, which ones do humans really have? And the answer is actually kind of both, right? It's a mix of both. There's this idea of exponential discounting. In other words, that as we go in the future, things become less valuable. But there's also this sort of discrete jump, right? Now in the future, there's usually sort of this big sort of drop off immediately, and then exponential sort of takes off or takes over. So it's a little bit of mix. So you'll hear the term exponential discounting or present bias discounting. In reality, humans have a little bit of both kind of traits. Well, let's go ahead and get you involved a little bit here. So let's go ahead and sort of ask ourselves, well, okay, how much do we discount, right? And I failed to mention this whole idea of discounting in the future and present bias is a part of a branch of economics called behavioral economics, which studies how people behave and make decisions and that may not necessarily always be sort of economically easily explained by traditional economics, and so behavioral economics has long looked at this idea of saving and procrastination. So anyway, but this is an example that now I want you to sort of just play around with as well. So get yourself just a piece of paper and then let's get the answers to these questions here. So imagine you choose between receiving $300 immediately or another amount 6 months from now. What would the future amount need to be to make it as attractive as $300 immediately? And so write down the amount, right? Okay, let's see, 300 immediately or something in the future. Okay, I'm going to write down something. I hope you're writing down something too. Okay, so there we go. And let's do part B here too. Same kind of question, right? See, 300 immediately or another amount 1 year now, but it's 1 year now. You're making you wait another for a whole year. What would the amount be? And I'm going to write down, say, a number. Okay. And so, well, I mean, I've done this with the adult teachers and students. Some of my students, I've done it with them. Well, these our answers reveal how we discount in the future, right? So, for example, if you take the amount 300 and divide it by the amount you wrote in part A, so I wrote 450. So 300 divided by 450, I get that's well, I guess that's 2/3, so 0.67. So that's telling you how much a dollar received in 6 months is worth to you today. So for me, in my answer of 450, I took 300 divided by 450, it gives me 0.67. It's saying that if you gave me a dollar 6 months from now, it's only worth 67 cents for me today, right? See, that's the problem, and it gets worse, right? Because then for a full year I wrote 600, and so if you took 300 divided by the 600, I get 0.50 cents. So a year from now, right? If you give me a dollar a year from now, that's only worth 50 cents to me today. And see, this is why it's really hard for people to sort of save, because when I do this test, people give these kind of numbers. You say, whoa, well, how can you motivate people then to save, right? When things are so much in the future. And so this is the problem that we all face, right? Is that because the reward to saving is the future, and because we discount things heavily in the future, it's really hard to sort of get people to save. And so we have to realize that we are trying to overcome human nature, right? We're trying to overcome people. So the bottom line is that when we talk about compound interest and we talk about savings, right? it is a hard topic because number one, the idea of compound interest is something that the kids need to sort of understand and be able to calculate those kind of things. But it is an incredibly important topic, and we really do have to help the kids understand. Okay, it isn't a bad thing, right? If you had your discounts and you found out the discount rates were really really high in the sense that people were discounting things in the future a lot. It just illustrates how difficult it is to get people to save. Well, there are lots of resources on savings and things, but hopefully this lesson is giving you some ideas of some of the things that I think are important. I think it is important that the kids can understand the idea of compounding. It's great if they can do some of the calculations on their own. Your rule of 72 is an important important rule of thumb that is actually very useful in sort of understanding things for retirement and whatnot. And then lastly, understanding that the human nature of why saving in itself is so difficult. So anyway, hopefully, we've been trying to keep these videos to sort of a reasonable length of time. Hopefully, you've come away with some things, and you will see me again when we do insurance, I guess. And I'll be doing the insurance game at that time. So until then, I hope you have a good boot camp.